Hello students, welcome back to CLARI Concepts, Unleashing Conceptual Learnings. Visit our website clariconcepts.com for more such conceptual videos. Today we will be talking about the numerical examples on the topic called capillary rise and fall. So those of you who have not yet viewed my lecture where I taught about capillary rise and fall, the theoretical aspects and its derivation, first I request you to go through that lecture and then come back to this lecture of numericals, right? Okay, let us solve the first numerical. First let me take the pen tool. Alright. Calculate the capillary rise in a glass tube of 2.5 mm diameter when immersed vertically. In first case is water and then in second case is mercury. So you have been given a glass tube which is of diameter 2.5 mm which is immersed first in water. You have to find the capillary rise, and then when it is immersed in case of mercury, you have to find out capillary fall, right? Take the surface tension coefficient of water and mercury to be 0.0725 newtons per meter and 0.52 newtons per meter respectively, and in contact with air mainly. The specific, now see, surface tension coefficients is not of one fluid, it is the property of two different fluids like water in air, that is 0.0725. Water in other gas will be different, right? So here is water in air and mercury in air, that's why it is saying that in contact with air. The specific gravity of mercury is 13.6 and the angle of contact for water and glass is 0 degree and that of mercury in glass is 130 degrees. Now see what is given to you. Let me first take the first case. I will put the given data. First is diameter of tube which is 2.5 mm. I will need to convert this into meter. So I will use these, I will divide it by 1000. So I will take 0.0025 meters. You check how you will check. You take decimal to 1, 2 and 3 places. So 1, 2 and 3. Yes. Now you have been given the surface tension coefficient of water and mercury to be this. So I will put sigma, but I will use W for water. So surface tension coefficient of water in air which is 0.0725 newtons per meter, and that for mercury I will use sigma m which is 0.52 newtons per meter. The specific gravity of mercury, so Sg of mercury is equals to 13.6, and the angle of contact for water I will put theta w basically for water which is 0 degrees, and that for mercury which is 130 degrees, right? Now let us first solve the case one by one. I will first use the case of capillary rise when the glass tube is immersed in water. So we know that in the previous lecture that the capillary rise will be equals to that, let's say HW is capillary rise because I am putting glass in water, that is equals to 4 sigma cos theta divided by rho g d. Now see what are all this number. Sigma is the coefficient of surface tension between the two fluids. Here it is water and air, so I will use this for water. Theta is the angle of contact between that. So if you remember, we had this tube and then this tube is immersed in the water beaker and you have this meniscus, right, the water, and this meniscus has this angle, this theta. Theta is known as angle of contact. Yes. So here I will use angle of contact for water. Density rho will be again for water because fluid is water, and diameter is for tube and g is known to us. So now we will have all the values, we will put the values. I know 4. What is sigma w? 0.0725 into cos theta w is 0 degrees, cos 0 divided by density of water. See, you must know the value of density of water because many times this will not be given to you in the numerical, but it is expected that as a student you know the value. It is 1000 kg per meter cube, right? Density of water is 1000 kg per meter cube. So I will use this 1000, and then g is 9.81 and then d is 0.0025. Let me calculate this. So I will get 4 into 0.0725. Anyway cos 0 is 1, so, and then divide by 1000 and divide by 9.81 and divide by 0025. This is coming out to be 0.0118 meters. If you want to find the value in mm, you will multiply it by 1000. So HW will be 11.8 mm. You see, This is the answer. So capillary rise is 11.8 mm. Let me check whether the answer is correct or not. Perfect. This is the right answer, right? Now let us take the second case wherein my fluid is mercury. So now capillary fall will take place, right? So capillary fall will be equals to, again the formula is same, 4 sigma cos theta by rho GD. What you need to do is, H will be for mercury, so I will put HM. Again sigma is for mercury, HM, rho M. Theta is for mercury, rho is for mercury. Now density of mercury is not given, but you have the specific gravity of mercury. Sg of mercury is 13.6. I hope you are aware from the fundamental principles of fluid mechanics that when specific gravity is given to you, you can easily find density of mercury by multiplying specific gravity with the density of water. So that is 13.6 into 1000 is equals to 13600 kg per meter cube. So you can put this value over here. So let us put all the values. For sigma for mercury is 0.52. 0.52. Cos theta for mercury is 130 degrees. And then rho m is 13600, which we have already found out. G is 9.81. Diameter is 0.0025 meters. Just calculate the answer. 4 into 0.52 into cos of 130 degrees divided by 13600, 9.81 and 0.0025. You are getting minus 4 into 10 raised to minus 3 meters, or you can say it is minus 0.004 meters, H mercury. Now what does it mean? If you convert this to mm, you will multiply it by 1000, you will get H mercury to be 4 mm, minus 4 mm, sorry. So what does this minus mean? Minus means that capillary fall has taken place. So the depression of the mercury level inside the tube will be 4 mm. So this is 4 mm capillary fall. So if you do the diagram, you have the beaker, and if you have mercury filled, and if you just insert this glass tube, what will happen is mercury will be up to this level in general fluid, let's say, and here it will be of this level, somewhere over here, right? So this depression, so here will be mercury. So all of this is filled with mercury. But here is the depression, this is your HM, and this value is around 4 mm. This is 4 mm. Clear? So I hope you understood how to solve the examples of such kind of numericals. So second numerical we have is the capillary rise in glass tube is not to exceed 0.2 mm of water. So let me just take the pen tool. Okay, what it is saying? The capillary rise in the glass tube is not to exceed 0.2 mm of water. So you have been said that maximum capillary rise should be 0.2 mm, right? Given data. Determine its minimum size given that the surface tension for the water in contact with air is 0.0725. So sigma is given to us 0.0725 newtons per meter, and the angle of contact for water and glass is 0 degrees. So see what they are asking. Again I am repeating the question. The capillary rise in a glass tube, they have been given a tube. They have this tube, okay, and they have this beaker where the water is filled. Okay, and they are saying that the capillary rise, because we know that when the glass tube will be inserted in the water beaker, the water will rise. They say that capillary rise should not be greater than, let's say this is H, they should not be greater than 0.2 mm, right? So they are saying that angle of contact of water is given and sigma is given to you. Determine the minimum size. Till what minimum extent the diameter should be kept. So they are asking you to find the diameter, D, right? So smaller the diameter, the height will be larger. So what will be the minimum diameter? I mean, most minimal diameter will be the maximum height will be, wherein the height of capillary rise should be 0.2 mm. So let us now solve this numerical. First I will convert this mm into meter. I will have to divide this by 1000. So this is 0.0002 meter, right? Now let me use the expression of H equals to 4 sigma cos theta by rho GD, and H is given to me as 0.0002 4, sigma is 0.0725, cos 0 is obviously 1, and then rho is 1000 into 9.81 into d. So what is the value of d? Simply you take d on the left hand side, you take 0.0002 in the denominator and go for the calculation. You will get 4 into 0.0725 into cos 0 is 1 divided by 1000 divided by 9.81 and then 0.0002. Diameter is 0.1478 meters, which is 14.78 centimeters, because I am multiplying it by 100. Let me check whether the answer is correct or not. Yeah. So the minimum diameter that you can have is 14.78 meter, for which the maximum capillary rise is 0.2 mm. Now the moment you reduce the diameter below this, what will happen? Capillary rise will go beyond 0.2 mm. Right? If you increase the diameter, let's say 15 centimeter, say 17 centimeter, capillary rise will fall short. Right? It will decrease. Thank you so much. I hope you understood how to solve the numericals on capillary rise and fall. We'll see you in the next class.